And so, what we've been talking about for the last this week, this section 13, is trying to understand flows of different kinds, um, and they go from California aqueduct flows, which are uniform flow in a regular section channel, um, where the bed and the slope of the surface and the slope of the energy grade line are all coincident with each other, through gradually varying flows where that's no longer the case, but where energy is conserved nonetheless, and that's what we were talking about last time and what I want to finish off today. And then to rapidly varying flows, which are basically code for hydraulic jump, where we can no longer make the assumption that the energy grade line is continuous but has a discontinuity in it. And so that's kind of where we will go to today, I think. This is kind of where we are. And just to set the stage, maybe in recapping these things, it's useful to talk about the where we are with this. So what we've talked about so far, we certainly talked about uniform flows, which are the Chezy formula and the Manning formula. And we've talked, although haven't completed, talking about gradually varying flows, where they're defined in terms of this. And so today we'll finish out by completing what we need to talk about in terms of gradually varying flows, and also talk about hydraulic jumps, which is this final topic. But to set it in context first, in way of summarizing, let's just do this. So in terms of uniform flows, what our assumptions are, we've drawn this diagram, and basically a uniform flow is where the bed and the water and the energy grade line, this is the hydraulic grade line, and this is also my little notation for free surface is this. Don't really know where it comes from actually, but actually this, let me do this vertically. And so by definition, y upstream and y downstream are the same. Oops. They're equivalent to each other, and in that instance the slope of the bed, the slope of the energy grade line are all equal to each other by definition. And if that's the case for uniform flows, then by definition we can get the velocity as merely a function of this scaling coefficient k, which is 1 for SI units and 1.49 for feet per second, a Manning coefficient, the hydraulic radius raised to the power 2/3, and the slope of the bed raised to the power half. Whoops. And if we want to get flow rate, we can get a velocity times the cross-sectional area. We can define some channel sections which are optimal, which give the least resistance because they're basically maximizing maximizing the hydraulic radius, I guess, and also for where this is just the section, and I guess also for a circular section where this height y is equal to the actual radius of this. B is equal to 2r in these cases. So in those cases we can merely write that behavior as that. And if you recall, for all of these, we defined a parameter, a new parameter, which if we look at, say, gradually varying flows, in other words, GVF, where the change in y as you go in the x direction is much less than 1, but where it's not equal to 0. In this case, because the height of flow upstream and downstream, if this is the x direction here along the channel, doesn't vary, then by definition dy dx is equal to 0. If that's not the case, as is in the case for these gradually varying flows, you have a slope of the bed, which is still S0. You have a slope of the water surface relative to that bed, where the upstream and the downstream depths are different from each other by definition. That's not horizontal. And also the energy grade line, which has this slope, which we call SF still, as in this. Then in that particular case, SF is not equal to S0 because of this, and the arguments we've made before is if this is smaller than the upstream, then the velocity here has to be larger than the upstream, and so the v squared over 2g term, which is what this is, has to be larger downstream, so it's certainly not constant. And in that particular case, what we could do is we could take the sections, and we spent all day last time doing this, and you take the section in perspective. This is the flow section, and what we do is we take a unit width relative to the whole flow section, B. And in the whole flow section, B, we have this flow rate going, but in this small unit width slice, vertical slice, we have a flow rate per unit width, which we call Q. So Q equals flow rate, which is meters cubed per second per unit width. Bad writing on my chart, but that's same. And so what, if we do that, then what we spent last time doing was we can rewrite Bernoulli's equation, and we write it as the upstream energy is equal to the downstream energy plus the difference between the slope of the energy grade line minus the slope of the bed multiplied by the length over which that occurs. So this is this, oops. This is this downstream length as you go along the channel. So I guess length would be this length. And so what we did was we defined this new term, and we spent a little bit of time deriving it, but it was what was it? I can remember. It's the depth plus the flow rate per unit width squared divided by 2 times gravity times y squared. And this is the energy, and it's energy at point 1, and this would be depth 1. And I guess this would be Q1, but Q is constant as long as the channel doesn't narrow. It might get higher, the flow might get higher, but as long as the channel doesn't get narrower, then Q would be the same, but I suppose we could call it Q1, and likewise for Q2. And so the importance of that was, and this is what we were just getting to, was that we could look at this curve, which kind of explained many of the things that we were dealing with. And if we plot energy, so this energy term includes, what is it? This is the v squared over 2, so that we've said this comes from Bernoulli. So all of these components have to only come from Bernoulli. So this comes from the head loss term. It's an equivalent to it. This comes from the Z1 minus Z2 term, just so it rings a bell. And then, so this is the head loss, this is the Z term. So the other two terms are the pressure head and the velocity head. So this is the pressure head. This is equivalent to P over gamma. It's just a depth, right, if you go down into the section. And this is equivalent to V squared over 2G. You note that these are lengths. Of course, these are both lengths as well, so nothing's really changed. And so this is just Bernoulli written a slightly different way. And it's written a slightly different way so that we can draw a graph of the depth of flow versus the energy. What we're going to say is that the energy upstream and downstream is the same. It's not changed. And this important graph looks like this. This is the line, which is a 45-degree line, which is depth is equal to energy. And if you choose any particular flow rate that's going through this, then you can draw a curve by just choosing a value of Q, and for cycling through all the potential values of Y that you get. Start off with Y equals 0, and it'll be over here. And you'll end up with a curve that ultimately asymptotes to this Y equals E curve. And so what this says is that if you have a particular depth in your section, which is this, which for instance might be behind a sluice. So this is what I'm going to draw here. So this is the bed of the river. This is a sluice that you have upstream. And the water level you have behind this is this. Then this is the amount of energy that would be present within that flow. If this is the amount of energy that's present in the flow, then downstream, if energy is conserved, then the elevation downstream then has to be this magnitude here. So this would be Y upstream, this would be Y downstream, just like these two components here. And so it's a figure that allows us to be able to understand why the flow might organize itself in these two potentially different ways. Both with the same amount of energy, but one with a very deep flow that's moving very slowly by continuity, and one as a very shallow flow that has to be, by definition, moving much faster. Even though the volumetric flow per unit widths of the channel are the same in both cases, one by virtue of the fact that it's tall is going slowly, and one by virtue of the fact that it's shallow is going much faster. And so last time what we did was we also talked about what this curve meant, and so this is a unique point here. This end of the tip of this nose is a point which is the critical depth, called Y sub c. And this critical depth occurs at an ordinate which is equal to an energy that's equal to 3 over 2 times YC. So if you know what the critical depth is, then the energy associated with that is always 3 over 2 YC. And the other important parts of this was that since we define the Froude number, as the velocity divided through by the wave velocity, and the wave velocity is in a shallow water channel is equal to gravity times the depth of the wave. When this is equal to 1, it means that the flow is going exactly the same rate as a ripple from a pebble will be traveling upstream, and so to a static observer it looks like that wave is not going anywhere. And so it can't communicate. It's on the cusp of not being able to communicate what's going on downstream to what's going on upstream. So they're completely unconnected in terms of no information flows between those physical states. And so the final component is that this point here represents a Froude number of 1, critical flow, as in Y sub c and E sub c. And this up here would be everything, actually everything above this line, getting a bit complicated, would be for Froude numbers less than 1. If you've got any space on this, I don't have much space. And everything below this line would be for Froude numbers greater than 1. Yeah. Yeah. Okay. That's because I'm an idiot this morning. It's fine. Thanks. More things I've done wrong this morning?
On the 45 line where it says
y equals y. Yes. Yeah. It's 45 degree line. So the two axes, I guess I could make it bigger, right? Because this.
Yeah, like that right behind it equals oh, that's a y.
This is y. Yeah, it's a y. Can you see that? I know. It could be anything, but it is a y. Yeah. And so this line here, okay, Alan, yeah, shoot. Yeah, go ahead. I'm listening.
The hydraulic grade line is not parallel to the slope of the bed.
This one here?
Yes.
No, it's not.
But what about the energy grade?
No, probably not. I mean, it looks like it is here, but it doesn't have to be. It's just a quirk that's drawn that way. There's no reason why it should be. Because you could imagine that you could choose this y to be anything you like, and this then scales with velocity squared. And so these will be linearly related, right? Because this is y, so we know that velocity times y1 equals velocity 2 y2. No, the short answer is it doesn't. They're not parallel. None of the three are parallel. And I would write that down here as well if I'm not sure we ever gave a term to the hydraulic grade line. S0 for the base, SF for the top part. I don't think we had anything. If it was SH, then if you want it, then this is also not equal SH. And the other thing I was going to put in here, so everything above this point here, this is subcritical for obvious reasons. Subcritical flow. And everything below this point here would be supercritical. And if you want a diagram of what those look like, supercritical, well, you have it here. This is supercritical. Shallow and fast. This is subcritical. Deep and slow. And so that's actually what we need to understand. And so what we'll do today is, since we're still really talking about gradually varying flows, which are these, GVFs, we'll talk about how to use this diagram to be able to do the things we've just talked about now. And basically what we're attempting to do is we're trying to explain why the fluid might choose to reorganize itself in two different ways, upstream and downstream, because it has this extra degree of freedom, which is the free surface, which defines how deep it is. And of course that facility doesn't exist either in pipe flows, where you fill a section by definition, and so there is no room for changing the cross-sectional flow area, or in external flows, where you think that you might have that capability, but really you just have this one fluid that's going around this water tank, and so it's got all the fluid outside that it's pushing against. Here you have water, which is a relatively dense, consistent fluid, against air, which is pushing against, which it can push against much more easily. Of course, we completely ignore the fact that there's air flowing around the water at all. We don't take it into account in any of our considerations, because the water has so much more momentum and energy associated with it than the air that surrounds it. So that's kind of a summary of where we are with this. And so what we'll deal with today is we'll go back to talk about gradually varying flows. And we'll note that gradually varying flows are where the upstream energy is equal to the downstream energy. And when we talk about rapidly varying flows, of which the type is the hydraulic jump, where you go from what must be a shallow flow here, which must be supercritical, to a subcritical flow. It's deep and slow, so slow but deep, and shallow but fast. And in that particular case, we'll find out that there's energy lost within the system because there's lots of turbulence in this region. And in that case, we don't write the energy as equivalent to each other. And so the ramification is that when we draw this diagram of energy versus depth, this 45-degree line, we no longer link the upstream and downstream on this part of the curve, but we go on a curve that does this. So we'll get to that. Maybe we'll get to that, maybe not. Okay? But the important thing today is to try and understand exactly what we're talking about in terms of gradually varying flows. And the key is this. And there's a couple of examples in the material that we didn't cover the other day. And let's just zip back to that. This is our derivation for this. You'll remember that. We decided that from this equation there were 3 roots. Only 2 of the roots are real. One of the roots is negative. Negative depth is nonsense, and so we ignore it. And that physically we can define the coordinates of these points by looking for the minimum of this nose here. And we've defined the ordinates of that as this exactly here, right? And it also exists at the Froude number of equal to 1. So that's what we've just summarized. So let's put it to use in trying to figure out exactly what's going on. And I don't think we need to do any calculations here. We just need to talk in concepts of what's going on. So let's talk about this idea where we have a sluice with an underflow around the sluice. Let's make some assumptions that it's inviscid. Inviscid means that the energy grade line is constant. So whatever this energy grade line is, because there's no energy lost within a system by definition. In other words, the HL term is, since we're really just rewriting Bernoulli's equation, we're just saying that the head loss term is 0. If the horizontal bed of flow is horizontal, then S0 is equal to 0. And so both of these both of these terms in Bernoulli, actually I say Bernoulli, but it's actually the energy equation, right? It's the 1D energy equation. So it's Bernoulli with the head loss terms added to it. And so this is where the Z1, Z2 term resides. It's equal to 0 here. And in the energy term, this is where P over gamma W, which is equal to Y. And this is where V squared over 2G reside. They both have the same units. And so what we could do is if we choose a particular flow rate, we have a flow rate going through this, which has to be the same both upstream and downstream. Then we can choose this value of flow rate, plug it in here, and cycle through values of y which start off at 0 and which go up to whatever number we want. And if you plot all those points, then you'll end up with this one curve here, this middle curve. So if you do that, you'll end up with one curve for a given value of q. And so you end up with this energy depth relationship. And so what that tells us is that if you draw this depth across here, this is the energy that's associated with this. And so what we'd know from this is that if it's going from, this is subcritical upstream, right? It's above, this is the nose, the tip of the nose. This is subcritical, everything is above here. Is it says that as it reorganizes the flow, it's required to reorganize flow by the fact you have this obstruction here. It has to be coming out here faster in terms of velocity, but actually with the same volumetric flow rate because continuity has to prevail. And continuity is the flow rate per unit width, and it's not getting any narrower into the page. So that means that if it has the same energy as you go across these, then the depth downstream we could calculate would be y2. And that comes from that. And so we could do a couple of things with that. So that's really all it's for. It allows us to be able to say something about the system. Yeah, okay. So what happens now if we do two things? If we raise the upstream level in the flow. So in other words, y1 would get larger, but if we keep q to be the same value, so we don't change the value of flow, what would happen? So initially our system was here. We're going to raise this value up some amount, but keep the flow rate the same. So in other words, if that's the case, then we started off exactly on this curve here, right? Is this right? This was us. So we're going to raise the level up from this to some new amount here. So this is the amount we raise it up by some amount. What's going to happen? So if we're flowing at this rate here, this is now our top, but the flow rate still is the same amount. So in other words, the only way that this would be the same amount, you think that if you raise the height here, you start spilling water faster. So the only way we can control that is by probably dropping the boom here to be able to keep Q constant. But because we've raised here and we're still on the same curve, so we still have to be on this curve here. And so instead of being at this point here, the new flow rate, sorry, the new downstream height, instead of being, instead of being this amount, this was the original one. I can't draw it very well because it's too finely resolved. Will be this height. So this will be, if you like, y1 prime. So this is prime for this first one. No, sorry. Prime for this first one. And the value for y2 prime will be this. Because we're still on the same curve, so in other words, you still have to be on the same Q equals whatever it was before. But now, because the energy here has changed to this amount, then the appropriate level is going to be this. And so, as we've raised the upstream level, we've had to drop the sluice down to keep the flow rate the same, and as a result, the water coming out of the bottom is thinner. It's less shallow, but it's faster, presumably. Even faster because it's the same flow rate. Okay? So that's just how we're going to use the curve. The second thing we could do, so if everyone's okay with that, yeah? The second thing we could do is we could raise the upstream level just as we did before. But now, instead of regulating Q by dropping the sluice, just leave it as it was before. And so now we're going to start from this point here. We're going to raise the water level up here. We're going to leave the sluice exactly where it was before, but not by dropping it. And so as a result of that, Q1 goes to, is it down on here? This increases. So the flow rate increases as a result of that. So now what's going to happen, instead of being on this curve, we have to do the calculation for all the different potential heights we have in the system, and this will be the new curve we get. The new curve will be inside the old curve, which will be this one. So this is Q prime prime greater than Q0. So in other words, let me just raise it up here so we can see both parts of this. So we're raising the upstream level. We're not shutting down the boom on it, and so the flow rate's going to go up. So now if we use a different value of the flow rate in this expression, we'll get a whole new curve of y versus e, which is this one. And so now, at this upstream level, we're still at this point y1, which is roughly the same as y1 before, because all of these points are constrained by this y, this y equals e line, y equals e line. And so it'll be this new number. It happens to occur with the same energy upstream and downstream, and so the new depth downstream is going to be this point here. And so we can use that to calculate what the reorganization in the system is. And so that's really all we're attempting to do. Free surface flows, they have an extra degree of freedom. We don't know whether it will be a deep, slow flow or a shallow, fast flow. If we have some constriction in the flow channel that allows us to divide those between those, we know that upstream and downstream, they have to be at the same value of energy. And so if we know the upstream magnitude and we know the flow rate, then we can calculate what the downstream magnitude would be, or vice versa. If you know the flow rate and the downstream magnitude, you can calculate your ordinate on this point, and you can figure out what the height is upstream. That's it. So that's all we're using this for. And so this is just a convenient term to use to be able to think about the behavior, because it allows us to plot it as a single variable. All right? So that's the important features, I would say, of that. All right. So let's make some suggestions as to some other behaviors. So you can apply it to a whole host of things, but here's one other question. How do you know if you have upstream flow, which is, in this case, flowing at some flow rate, and that you know the upstream depth, and it's happily going down a channel, and if we look at this channel, all we know is it's 2.3 feet deep, it's happily going down, it's got a horizontal bed, and so the question is, if it goes up a ramp, and the elevation changes, what will the depth be at this, bless you, what will the depth look like as you go past the top of this ramp? So the question is, what is the depth of this flow at the upstream location? And so what you could do is, if you know the flow rate, if you know the upstream depth, certainly you can calculate from energy y plus, what is it, flow rate squared over 2gy squared. Oh, how are your knuckles? You can cycle through this from y greater than 0 to y less than 4 in this particular case, I guess, right? So if you cycle from these, you get a curve. This is the curve you get. You know that upstream at 2.3 feet, this point here, this is the energy. You go down here, you find out that as you go down here, then it potentially, if the height of this ramp didn't change, then it could potentially be flowing at this height downstream if it was just horizontal. But that's not what you're being asked. You're being asked here, what happens if you go up a ramp to a new height? So in other words, this is our Bernoulli equation. These terms are P over gamma plus V squared over 2G. This term here is Z1. You know, these two Z1 terms are usually included in this, what is it, S0L term, but we're dealing with them here. And whatever the head loss is within the system. So we'll take this head loss to be equal to 0 in this case, by definition. So the fact that we're going up from Z1, which is equal to 0, if we take this as our datum here, the fact that we're going up to a new height, Z2, which is equal to 0.5 feet, then it means that what we can do is that we can go from this 2.4 magnitude, so this is 2.3, this is the y is equal to E line, depth is equal to energy line. So since this is 45 degrees, it's almost on this line. It should be about 2.3. It's actually a bit more. It's 2.4. And so if we go an amount which is 0.5, which is this 1.9 here. So in other words, if we go an amount here, which is 0.5, which is exactly what, pictorially or graphically, exactly what this is, then we could imagine that the downstream depth as you go up this ramp is either this number or it's this number. Right? So we've gone 0.5 here. The energy has changed by 0.5 because we've gone up in elevation. In other words, we've had to subtract off this number here. So then the question becomes, is it going to look like this, which would be a little dip in the free surface like this? Or is it going to look like this, which is a big dip in the free surface like this? And so that's the question. And so how do we rationalize that? Well, to rationalize that, I think it's relatively straightforward. The rationalization is basically this. To get from this point to this point, we have to go through this nose along this trajectory, right? Because everywhere we go downstream, as we go along this corresponds to a particular depth. So it means that to get from this point to this point, we have to go through a depth where the Froude number is equal to 1. And so if by going up this ramp, we only go monotonically down a small amount of depth here, then we don't physically go through this nose where we go through this critical Froude number. And so if we only have a ramp here, what we do is we would end up at this point here. So if the ramp, ignore this little hump here, if only the ramp is here, then the free surface will look like this, which would be this number here. But if you want to be able to get to this point here, then you have to allow the water depth to change so that, I guess, this ramp height would basically have to be this length here. So whatever this length here, well, I won't use L. Let's choose X. So in other words, this ramp height here basically has to be X to be able to get us to this point. And then on the downstream side of this, we keep on going down this. So in other words, we're starting off at this point. We're going, I wish I had a different color. We're going down the curve. It's the same flow rate as we go around here. We get to this point here right on the top here. And then we keep on going down the other side to get to this component here. And so this would be, by definition, what we've called here, everything above this would be subcritical. Looks like subcut, but it's not, it's subcrit. And everything below here would be supercritical. And so if you looked at these flows, this flow here for sure is subcritical. With this free surface here, it corresponds to this. This would also be subcritical, but it would have this dip in it. Seems kind of strange. You go up a ramp, so the water height, the height of the bed gets higher, but the absolute depth of the water, in an absolute sense, is less than it was upstream. Right? This is low. So it's kind of curious. But it's still subcritical. If it goes up a ramp to be able to do this, then it, again, perhaps even more surprisingly, is it makes this transition and it becomes supercritical, or it could become supercritical on the downstream, because it's gone through this nose, it's gone through the critical velocity of flow, and so it's free to be able to get to this point. Otherwise, it can't get to this point unless it has this. Yeah. So that's kind of the use of these diagrams, is to be able to say something about that, right? Yeah.
So is the reason that even though it goes up in elevation, the energy goes down? Is that because it's being subtracted from the equation down there? Because the energy is shifting.
Oh yeah. Well, the energy, yes, the energy has changed. So I guess in this case, E1 plus Z1 equals E2 plus Z2. Yeah. So this is the relationship, and so this is always 0 in our particular case. So the energy, this is the equivalent of the. I mean, it's not a continuous rise in the bed; it's just an incremental jump in the bed. Yeah. So So it's the energy change. And so it has to include the elevation, the energy including the elevation term. Okay? So that's kind of how we'd like to use these behaviors. Oops, that's not right. Okay? And so you can look through the working to be able to figure that out, but I think understanding graphically what's going on, I think, is perhaps the more important part. Yeah, and so, yeah, I don't think we need to perhaps say any more about it. Of course, we've talked about a flow which was upstream. I guess we go right up to here, in this case here. We've talked about a flow which started off upstream subcritical, and as it goes downstream, it could be subcritical or supercritical. It could also be the other way, as in a hydraulic jump, that it starts off supercritical, shallow and fast, and it has the potential to be able to do something as it changes elevation. And so the appropriate curves for this would be to do exactly the same thing. You know what the flow rate is here, so you can calculate, that's a Q, you can calculate the energy equation from the depth plus the flow rate squared over 2 times gravity times the depth squared. So you can calculate this for all the values of y. You get a similar curve. Upstream, you start off at this particular elevation, which would be this height here. And the same argument. As you change the height of this bed by 0.5 feet, so you've changed your energy from this point here to this point here by 0.5. And so as you go upstream, you're still supercritical because you're below this point here. But the depth has actually increased, and therefore by definition the velocity has decreased. It's still greater than the celerity wave velocity because you're still at a Froude number that's greater than 1, but you haven't gone beyond this nose. To be able to get to this point, you have to be able to do the same thing. So you'd now need a bump in this system to be able to get to this point, which again would have to be x height relative to this, or let's call this whole thing actually x, right? And so in other words, you'd have to have a bump here, which is this, to be able to do that. So in other words, to be able to get to this nose here, you have to be here, and then on the downstream, I guess you could argue that it could choose to do either of these, right? It's sitting on this point here. It's like having a ball bearing on top of a hill. It can roll down this side, or it can roll down the other side. And so now it's at this kind of critical point, and it could either choose to go up here, or it could choose to go down here. And there are a whole series of rules to suggest why it should do that based on the bed shape, etc., which we won't really go into. But to be able to get to this point, it has to go through this critical point unless you change the velocity and switch on to another flow regime. So that's kind of the ins and outs, if you like, of understanding why we want to use the energy equation. The very last thing that we alluded to, I'm going to leave that at that. And so we won't do this other material. The very last thing that we alluded to was that, I suppose this is Evelyn's question, that should actually be strictly speaking. In all of the cases that we've talked about, we've said that we can come down through the system and the energy in the system should be the same. It should be on this vertical line. And so those are the cases for what we've called gradually varying flows. So gradually varying flows mean that the slope of the free surface, the depth change, is really very small. How small? Quite small. But the other forms of flows that we get that are kind of exciting, which actually are epitomized in the whitewater videos that we looked at for the New River and others, are that all of a sudden, instead of this being a gradual transition, so remember that in this system that we just looked at, we had an upstream flow which was quite deep, and it would change to some other flow as you went downstream. Rapidly varying flows, as their name would suggest, means that the flow goes from being something to something else, basically in no distance at all. In other words, when this number is now quite large compared to this. So this is a very smooth transition. This is a very rapid transition. And we don't have a great deal of time to be able to talk about that. But to make the point that when physically what we'd like to do, and I'm not sure it is much use to be able to look at these expressions. Physically, it's epitomized in this figure here, and that is that when we go from an upstream flow which has organized itself in some way to a downstream flow which has organized itself in a rather different way, and it makes that transition over a very, very short interval, which is this, then no longer can we say that the energy grade line is continuous. It has this discontinuity in it. And it's really because that we're using up a lot of energy in the turbulence that we're developing at this particular location, because something has triggered this flow. And we can define a new quantity, and this new quantity that we can define is momentum. And I'll just scroll back up to the previous page. If you remember last time, we did look at conservation of momentum when we looked at uniform flows. And we saw that because the upstream depth on a uniform flow was equal to the downstream depth on a uniform flow, that the forces that were applied both upstream and downstream on this little free body diagram that we had, if you remember back, this was two sessions ago, was that these were exactly equal to each other, and so these two terms would cancel. If this depth upstream and downstream is no longer the same, as it would be here, then the forces acting upstream and downstream are not equal to 0. This is not equal. F1 does not equal F2, or negative F2. Then this term is not 0, and we end up with extra terms left. So before, conservation of momentum threw these terms out. Now if we do conservation of momentum, we get a significant equation. And this equation looks like this. This is momentum. It looks like the Bernoulli equation, but instead of a length term, it's a length squared. It must be momentum per unit mass or something. I'm not sure exactly how to rationalize the units, but it's just another term. And so if we can define how momentum changes within the system, we think that momentum should be conserved as you go from upstream to downstream. So in other words, we could write uppercase M1 is equal to uppercase M2 by conserving momentum. We have the energy equation. This term here is E1. And this term here is E2. And conservation. So if we use these three equations, energy equation, which is Bernoulli's equation with the head loss term, momentum, which is really just F equals ma in this term, and continuity. And if we use those, then again the graphical description of what we have in these systems is basically this. We don't conserve energy because we go from upstream energy to downstream energy, and it's over a very short interval, a disappearingly small interval. We have a head loss that happens instantly. And so all we can do is we can look at the upstream velocity here, or depth rather, by plotting momentum versus depth. I don't know whether this has a 45-degree line in it or not. And so we could plot this curve if we know what Q is, and we cycle through all the potential values of our depth. We get this curve. If we know what the upstream supercritical velocity is, then we anchor ourselves at this point here. If we'd anchored ourselves at this point here and we conserve momentum, then we know that the downstream depth has to be this. And so we know those two depths because we admit that we conserve momentum as we go across this thing. Momentum upstream and downstream is the same. The consequence of that is that then if you plot the values of the energy relationship, again by doing the same, we have the same flow rate. You cycle through all the potential values of y to be able to get this curve here. Then where this matches up is that we now know the upstream velocity, depth rather, which would be this point on this curve. We also, as it turns out, know the downstream depth, which would be this point here. They're no longer on the same energy lines because of what we've said about the disconnection as we go from upstream to downstream in the energy grade line. And as a result, the offset between these two energy points would be the head loss within the system. So that kind of defines the ultimate, the final component that we'll deal with. Well, we won't deal with it because we're finishing now. But the behavior that we see in hydraulic jumps, where for no apparent reason, it changes from being this behavior. Let's do it here. We looked at it. I guess we do, yeah, fine. So I don't want to do this. Some equations, let's not do those, we've seen this. But as we zip through here, it's working quite nicely. It gets the right place. So this is just a laboratory flume with a given flow rate going through it. It has a certain small slope to it to allow it to flow. And the idea here is that you have a given flow rate occurring within here. You change the slope and the flow rate until you get supercritical flow flowing within this depth, which you can calculate. And then, as a result of that supercritical flow, you allow it to develop this natural instability. So presumably now it's probably happily flowing. It's maybe subcritical. You can force it to be a supercritical flow by putting a sluice in the section. So it's subcritical below it, or was. You're going to wind down the depth of this sluice below it. And so downstream of it, to the right of the video, you get this behavior that coming underneath this sluice, it's going to be supercritical. You wind it down a little more, and a little more, and you get this behavior where it's really screaming out the bottom of here. So this is supercritical. It's subcritical upstream, presumably. This is supercritical, just as in the diagrams that we've talked about for the first half of the discussion today. But now this supercritical flow, for some reason, all of a sudden clicks over to subcritical flow downstream. And it's because of some instability that it can't retain itself. And it's basically the diagram that we just drew is it's going from this very high velocity shallow flow here to a much slower but deeper flow here, which is going from supercritical to subcritical. And the explanation, if you like, of that is really what we've just talked about in this. And that is that we don't conserve momentum. We do conserve momentum, but we don't conserve energy, because as we go across this portion here where we get this piling up of the wave, basically, as kayakers, whitewater boaters would say, this wave is, or this pillow, is as a result of this change from supercritical flow to subcritical flow. We rationalize it exactly because we know the momentum upstream and downstream are the same, but because of all of this turbulent flow that we're getting here, this dissipation of energy is resulting in this head loss that occurs within our system. That's where we'll leave it. All right, that's enough for today.